Welcome back to the Deep Dive. Today we are taking a deep breath and plunging headfirst into the high-voltage architecture of a vehicle that is, let's be honest, probably the least glamorous but mechanically the most brutalized on any road.
The hybrid cement mixer truck.
Exactly. And we're going to focus on just one component, the fuse, and show how this seemingly simple piece of metal is actually hiding some immense engineering complexity.
That's right. This deep dive is built around really analyzing the precise methodology needed for high-voltage fuse matching. We're looking at a specific case, a P2 hybrid plus what they call an ePTO, or electric power takeoff system.
And that's all on a 400-volt platform.
Right. And our mission here is to basically create a blueprint, a professional engineering mandate, if you will, to develop this capability from scratch. We're not just picking a fuse that works today. We're trying to extract the non-negotiable principles you'd need to guarantee safety. We're talking ISO 262622, but also power and maybe most importantly, long-term million-kilometer reliability in an environment that is just constantly trying to destroy every single component.
Okay, let's unpack that right away. We often talk about EVs in terms of speed, range, sexy features. Here, we're talking about surviving a construction site. Intense heat, crazy vibration, all while spinning 40 tons of abrasive material. So why does this specific duty cycle create such a fundamental problem for a fuse compared to, say, a normal delivery van or a passenger car?
It's the interaction of extreme load demands and a just incredibly hostile environment. We have two primary high-power systems running in parallel. This is what we call the dual load, dual power source problem.
Okay.
And their failure modes are, well, they're contradictory. You have the main traction drive system, that's the P2 motor helping drive the wheels.
Right.
And then you have the auxiliary upper structure drive, which is the really powerful electric motor that's spinning the mixer drum itself.
And I'm guessing the forces they exert on the electrical system are just wildly different.
Night and day. Let's start with the traction system. For the traction fuse, with this heavy, fully loaded truck, the core risk is something called thermal fatigue.
Okay.
Imagine the truck in a busy city or maybe going down a steep hill. The current doesn't just flow one way, it violently cycles. You might slam into a heavy regenerative braking phase, pulling, say, negative 200 amps back into the battery.
Pushing power back in.
Right. And then a second later, you're accelerating and demanding a massive boost of positive 400 amps. This cycle negative, zero, positive, over and over, hundreds of times an hour, causes this rapid, extreme thermal expansion and contraction of the silver fuse element inside.
So we're really getting into material science here. This isn't just an electrical problem. What does that constant flexing, that heating and cooling, do to the metal over months and years?
Well, if you could look at that fuse element under a microscope, that constant mechanical stress actually deforms the metal's crystal lattice. You start to get these microcracks propagating through the material.
And over months or years, the cross-sectional area of that fuse element effectively shrinks. Its internal resistance starts to creep up.
And higher resistance means more heat.
Exactly. You get a positive feedback loop of thermal stress, and eventually the fuse blows. But here's the key. It doesn't blow during a short circuit. It blows under normal working current.
Which is what engineers call nuisance blowing. And it has to be a devastating warranty claim. I mean, it looks like a quality defect from the supplier.
But it's not. It's a fundamental engineering selection error. It's a failure to account for that long-term thermal fatigue.
Wow. Okay, so that's one problem. Now pivot to the second, and you said even more violent, electrical challenge. The mixer drum surge impact.
Right.
I can just picture this. The truck pulls up, the driver stops the drum for a few minutes, and all that concrete inside, which is heavy, abrasive, and literally setting.
It coagulates, it settles, it creates this immense static friction. And when the operator tries to restart that drum, the motor has to overcome a massive breakaway torque.
And that takes a huge jolt of power. It requires a stall-like inrush current surge. We're not talking about a little spike. We're talking 5, maybe 8 times the rated continuous current. And unlike, say, a capacitor charging surge that lasts milliseconds, this mechanical demand can last for hundreds of milliseconds, sometimes close to a full second, until that drum gets spinning again.
So, okay, if the traction system is killing the fuse with 1,000 tiny thermal cuts over its lifetime, The mixer drum is killing it with one massive, repeated punch to the system.
That's a perfect analogy. That surge impact energy, even if the fuse survives and doesn't melt on the spot, it inflicts immediate physical damage to the silver element's crystal structure. It's just a different kind of physical damage.
And that drastically shortens its life.
It does, and you have to engineer for both of these simultaneously. And let's not forget the environment we're in. The power distribution unit, the PDU, can be running at over 100 degrees Celsius constantly. Vibration profiles are often 3 to 4 times more intense than passenger car norms.
And dust.
Pervasive, conductive cement dust that is just looking for any vulnerability, any crack to get into. This is, I would argue, the ultimate test for high voltage reliability in a vehicle.
Okay, that sets the stage perfectly. It's an absolutely brutal environment. So let's get into the strategic framework for how you even begin to solve this.
The first principle in this engineering blueprint, it addresses this dual challenge by fundamentally redefining the role of the fuse.
Right, and you have to start with this philosophical shift, which sounds completely counterintuitive to anyone who's ever changed a fuse at home. And that is, the high voltage fuse is not overload protection.
It is the absolute foundational mandate for high voltage DC system safety. I can't stress that enough.
Yeah.
In a modern 400-volt architecture, overload protection demanding more power than the battery can safely deliver for a few seconds, that's handled by intelligent electronics.
The software.
That's the job of the battery management system, the BMS, and the motor control unit, the MCU. They control torque, they manage current flow. The fuse's role is strictly as the absolute physical defense line. It is only there for one reason.
And what's that?
To react to uncontrollable current events, the events that bypass or just completely overwhelm the intelligent control loops.
So what are these uncontrollable events? What requires this hard physical stop?
They're faults that lead to instantaneous, massive current flows. There are really 3 primary scenarios. First, a hard short circuit. The positive and negative bus bars or cables directly touch.
The big one.
The big one. Second, a catastrophic internal semiconductor breakdown, usually an IGBT failure inside the inverter. And third, a wire-to-chassis short, which grounds the high-voltage system. These events require a protection response in the, 1 to 100 millisecond range. That's a time frame where intelligent software alone just cannot guarantee isolation.
So this architecture, it demands multiple layers of defense. The analysis calls this the protection pyramid, right? Yeah. And the fuse sits at the very bottom, guaranteeing that final isolation.
Correct. You need redundancy, both in time and in capacity. So layer 1, the fastest, is the BMS MCU software. It operates in the sub-10 millisecond range. Its job is predictive. It handles controllable overloads by actively limiting torque or issuing a soft shutdown command to the contactors. It's all based on its own measurements.
Okay, but if the software fails, or if the fault is just too big for a software-controlled shutdown, then we move to the next layer, the intermediate layer.
Which is the HV contactor.
A physical switch.
A physical electromechanical switch. It operates in the 10 to 50 millisecond range. It provides limited overcurrent cutoff, and it's effective, but it has one crucial limitation: a finite DC breaking capacity.
Meaning?
The energy of a DC arc is immense. If a fault current significantly exceeds the contactor's rated limit, let's say you ask a 2500 amp contactor to interrupt 5000 amps, the arc energy will cause the contacts to explode, vaporize, or just weld permanently shut.
Which is exactly why the HV fuse layer 3 is absolutely mandatory as the ultimate failsafe.
It is the last resort. It reacts to those catastrophic short circuits by physically sacrificing itself to isolate the energy source, the battery pack, and prevent thermal runaway or ignition. The key is that its interrupting mechanism is purely thermal and current dependent.
So it's immune to any control circuit failure.
Totally immune. And that provides the deterministic safety you need to hit something like an ASLD target.
Okay, so once we define the roles of these layers, we have to define the physical placement. The engineering hierarchy divides the fuses into A-class and B-class. What's the difference?
This hierarchy is all about ensuring selectivity.
Selectivity meaning only the right fuse blows during a fault.
Right, which minimizes downtime. The A-class fuse is the main protection. It sits right at the pack level, often integrated into the manual service disconnect, the MSD, or the battery disconnect unit, the BDU.
And its mission is to protect the whole vehicle.
Its function is to protect the main bus bar, the battery terminals, and the primary high-voltage harness leaving the battery enclosure. And because it protects everything, it must have the highest braking capacity. We're talking certified to interrupt 20 to 30 kiloamps at 500 VDC.
And this is the counterintuitive part. It has to be the slowest to act.
Right.
Why slowest? Wouldn't you want the main fuse to be the fastest?
You'd think so, but it comes back to selectivity. If a short happens downstream, say on the DC to DC converter branch, we want the B-class fuse on that branch to clear first.
Ah, I see.
If the A-class fuse blows, the entire truck is dead. That's a service call, a tow truck, the works. If the A-class fuse only blows after all the downstream B-class fuses have failed to clear, it guarantees maximum operational uptime and prevents a total loss of power for what might be a very localized fault.
That makes perfect sense.
Yeah.
So that brings us to the B-class fuses at the load branch level.
These protect individual, specific high-power loads. For our cement mixer, you'd have distinct B-class requirements. B1 for the traction inverter, B2 for the mixer motor inverter, B3 for the main DC-DC converter, and so on for other auxiliaries.
And this just reinforces that critical insight from the very start.
Yeah.
The mixer motor fuse must be engineered completely differently from the traction motor fuse.
Absolutely non-negotiable. An engineer cannot, under any circumstances, treat these as identical loads and just slap the same fuse on both. The B1, the traction fuse, it has to withstand that high-frequency, long-term thermal fatigue.
So it's all about that KC factor we'll get to.
It's critical. But the B2, the mixer drum fuse, has to resist the violent repeated surge energy, the I squared T. Its pulse rating and its fatigue criterion have to dominate the selection process. Failing to do this, to make that independent selection, it guarantees premature field failures within the first few 100,000 kilometers. It's a certainty.
Okay, so with that hierarchy defined, the real engineering work starts. We move to the hard math of component selection, and we have to start with voltage. We're dealing with a nominal 400-volt system. Why can't we just pick a fuse rated for 400 volts or, maybe even 450 to be safe?
This is a classic case where conservatism becomes a mandatory safety feature. The design principle is crystal clear. U fuse must be greater than or equal to 1.25 times U max system.
And that 400 volts is just the nominal working voltage.
It's just the average. The battery's open circuit voltage when it's fully charged and healthy is already higher, maybe 430 volts. But the real spikes, they happen during heavy dynamic operation.
So I'm imagining that fully loaded 40-ton mixer truck descending a long mountain pass using aggressive regenerative braking.
That's the exact scenario. During high state of charge, high state of health conditions, that regenerative braking energy pushes the DC link voltage violently upwards. Our analysis shows momentary spikes can easily reach 460, 470, even 480 volts.
So a 450-volt rated fuse is already operating on the ragged edge.
It's dangerously close to its physical limit for extinguishing the arc, especially when it's already hot from carrying current.
And what happens if the operating voltage exceeds the fuse's rated DC voltage when it tries to blow?
Catastrophe. I mean, literally. If the fuse tries to clear a short circuit at 480 volts, but it's only rated for 450, the air gap inside the fuse, which is designed to suppress that arc, it may not be large enough to break the circuit.
The arc just keeps going.
The arc will sustain itself. We call it refusal to open. And that leads to incredible heat, casing rupture, and a very real fire risk. This is why the engineering mandate for a commercial vehicle is an absolute 500 VDC minimum rated voltage.
And then you mentioned altitude, too.
Right. We have to account for high altitude operation. Above 2,000 meters, the air density drops, and that reduces the air's dielectric strength, its ability to insulate against arcing. Using a 450 VDC component in, say, Denver is absolutely prohibited by best practice standards.
So once we've locked in the voltage 500 VDC minimum, we have to tackle the current. This brings us to what you call the heart of commercial vehicle safety calculation. The golden formula. This isn't just, current divided by temperature. It's a rigorous multivariable equation.
It is. It's the synthesis of all those harsh realities the truck is going to face. The formula is designed to ensure the fuse's actual capacity, I fuse, is far, far greater than the load's continuous root means square current, I load arms, once you apply all the environmental and operational D ratings.
And the formula is I fuse is greater than or equal to I load arms divided by the product of a bunch of K factors.
KT, KE, KV, KA, and KC. The difficulty isn't the math, it's the conservative, accurate determination of those 5 D rating coefficients. That's where the engineering judgment comes in.
Okay, let's break down the most critical factors here, starting with KT, the temperature D rating factor.
KT addresses the thermal environment. A standard fuse you buy off the shelf is rated at a 25 degrees Celsius ambient temperature. But as we already established, the PDU in a cement mixer's engine bay can easily hit 100 degrees C or even 120 during a hot shutdown.
How does temperature physically affect the fuse's ability to carry current? It seems obvious, but what's the mechanism?
Well, fuses are fundamentally melting elements. If the ambient temperature is already high, that silver element inside is already closer to its melting point. It just requires less electrical energy or current to push it over the edge and melt it.
So in a passenger car, we might derate a little bit.
Right. But for 100 degrees C operation, the engineering mandate requires a minimum derating of kT equals 0.85. If you neglect this, a 500 amp fuse, which is designed to safely carry 500 amps at room temperature, might only safely carry 425 amps at 100 degrees C without degrading over time.
Okay, next up is KE, the terminal thermal conductivity. This factor deals with how well the fuse connection itself helps get rid of heat.
It's often ignored, but it's crucial. About 60% of the heat generated within the fuse element has to escape through its terminals and into the attached busbar or cable lugs.
It's a heat sink.
It's the primary heat sink. So if that thermal pathway is poor, the heat just concentrates inside the fuse. We look at the busbar connection. If the current density in the copper exceeds about 2.0 amps per square millimeter, that's a red flag for a hot spot.
And in this application, vibration must be a huge factor.
That's the critical part. Given the constant severe vibration, we have to anticipate potential micro-loosening or oxidation at that bolt connection over the vehicle's life.
And that loosening would compromise the thermal contact, trapping heat.
Exactly. So due to that high risk, the engineering mandate advises a very conservative factor of KE equals 0.85 or even lower, just to ensure the fuse element doesn't overheat locally because its primary heat sink is degraded.
So KV for cooling wind speed and KA for altitude are pretty straightforward adjustments for sealed enclosures and high-altitude operation. But now we get to the absolute game changer, the one that dictates whether the truck lasts 100,000 kilometers or a million. That's KEC, the cyclic loading factor.
KC is the lifeblood factor. It is. It directly accounts for that thermal fatigue, the microcracking we talked about right at the start. A standard passenger EV, which is maybe aiming for a 150,000 kilometer lifespan, might use a KC of 0.80.
Which seems reasonable.
For that application. But the cement mixer has to operate for a decade in these severe conditions. So to prevent that nuisance blowing, the fuse has to be significantly oversized.
And what are the non-negotiable KC mandates from this engineering analysis? What's the number?
For the main traction circuits, which see the most intense high-frequency current cycling, the mandated factor is extremely conservative. KC is less than or equal to 1.60.
Wow, that's a huge derating.
It is. For the mixer drum circuit, which experiences fewer cycles but that immense surge impact, the factor can be slightly higher but still heavily derated, typically KC less than or equal to 0.65. This low number ensures the element runs cool enough during normal operation that the physical stress from expansion and contraction is minimized over a decade of use.
Okay, let's make this real. Let's apply this extreme conservatism to the mixer motor fuse to see what it actually means in terms of cost and size. Let's assume the motor draws a continuous I load of 300 amps RMS.
Okay. So we use the mandatory conservative factors we just defined. Let's say KT is 0.85 for high temp, KE is 0.90 for vibration risk, KAV is 0.95 for the sealed enclosure, and then that critical KC is 0.65 for the mixer. We'll ignore KA for now just to keep it simple.
So if we multiply those K factors in the denominator,
Yep.
0.85 times 0.90 times 0.95 times 0.65, we get a combined derating factor of approximately 0.4724.
Correct. So the calculation becomes 300 amps divided by 0.4724. And this results in a required fuse current rating of approximately 635 amps.
Wait a second. Let that sink in. A component that only draws 300 amps continuously requires a 650 amp or maybe even a 700 amp standard size fuse. That's more than double the component size, weight, and I'm guessing the cost.
It is.
So as the engineer leading this development, I have to ask, does procurement ever push back? Why can't I argue for a 500 amp fuse to save space and money?
That is the crucial negotiation point in any commercial vehicle program. Of course, they push back. Engineers are always under pressure to optimize size and cost, but the KC factor is your warranty safeguard. It's your engineering shield.
Explain that.
If you give in and you drop that KC from 0.65 up to 0.75, your required fuse rating drops to around 550A. That's a significant cost saving on paper.
Right.
But it also means your internal resistance will be higher, the element will run hotter, and you are accepting a dramatically higher risk of nuisance blowing failure at, say, the 3-year mark.
Which costs exponentially more to fix in the field.
Exactly. The blueprint mandates this over-design because the financial risk of a field failure in a commercial fleet far, far outweighs the component cost savings. That 650 amp minimum is the engineering price you pay for guaranteed life cycle reliability.
So we've now sized the fuse, a huge 650 amp fuse, to survive that long-term thermal fatigue, but we still have that immediate threat, the massive surge impact from the mixer drum breaking away from that coagulated concrete.
Hmm.
How do we check that this oversized component doesn't still just blow during one of those intense startup pulses?
This is where our focus shifts from continuous current to pulsed energy. We have to check the fuse's mechanical tolerance to instantaneous heating. This is the I²T check. It's a pulse energy calculation. We have to ensure the energy deposited during that surge, I²T of the pulse, is tolerable.
So if we know the inrush current is, say, 8 times the rated current, so 2400 amps, and it lasts for 500 milliseconds, we calculate the energy deposited in that half second.
Exactly. And then you compare that against the fuse's inherent pre-arcing I²T, which is the energy required to melt the element. But here's the thing. A successful comparison only proves the fuse won't blow immediately. For commercial vehicles, that is completely insufficient.
Okay.
We have to apply the fatigue criterion.
This sounds like the invisible enemy, the thing that guarantees the failure months down the road. What's the physics behind this criterion?
That massive current pulse, it creates an instantaneous localized heat gradient within the silver element. Even if it doesn't melt, that heat shock causes a rapid temporary change in the crystal structure. Repeating this thousands of times throughout the truck's life leads to cumulative physical degradation.
Even if each individual event is non-fatal.
Exactly. The engineering mandate dictates that the sum of all expected pulse energy over the component's entire lifespan, that's sigma I²T of the pulse, must be extremely low. We're talking less than 10 to 20% of the fuse's inherent melting I²T.
That seems incredibly conservative. Does that mean 80 or 90% of the fuse's melting capability is just reserved, never to be used? Do engineers ever argue for pushing that limit higher to maybe 30 or 40%? To get a smaller fuse?
They do, especially in systems where the load profile is perfectly predictable and repeatable. But in this environment, where concrete consistency, ambient temperature, how long it's been sitting, it all varies wildly. That margin is non-negotiable.
What happens if you exceed that 20% cumulative limit?
You accelerate that crystal lattice deformation, and the consequence of error here is a component that, 6 months later, under a normal 300 amp stirring current, just opens circuit. The maintenance tech analyzes it, sees no short, and misdiagnoses it as a quality defect from the supplier.
When in reality, it was a selection error, a failed pulse energy calculation from months ago.
And that criterion is a direct defense against that misdiagnosis and that kind of premature field failure.
It's incredible. This whole calculation is really about modeling the thermodynamic longevity of a microscopic piece of metal under stresses that are both continuous and acute. It's a fascinating insight.
That's reliability engineering in a nutshell.
Okay, so moving from sizing individual components to ensuring system-wide safety, we have to coordinate the entire protection stack, the fuse, the contactor, and the cables. This means doing a rigorous TC curve coordination.
TC, or time current coordination, is the mandatory graphical analysis that ensures sequential protection. It's how we make sure everything works together. We have to overlay 3 key boundaries on a log plot to verify that the energy deposited during any fault is always interrupted safely.
What are the 3 non-negotiable curves we are analyzing on this plot?
First, the cable damage limit curve. This shows you the time required for a given current to thermally degrade the cable insulation to the point of smoke or fire.
The absolute do not cross line.
Exactly. Second, the contactor limit curve, specifically its maximum DC breaking capacity. And third, the fuse clearing curve, which shows how quickly the fuse isolates the fault at different currents. The fundamental coordination principle is simple.
What is it?
The fuse curve must sit safely to the left of, meaning faster, and below, meaning lower current, the cable and contactor curves in the short circuit region.
So if the fuse is too slow or too large, the cable or the contactor fail first. But there's a huge, dangerous gap in traditional architectures, which the white paper calls the forbidden zone.
The forbidden zone is probably the most critical safety blind spot in DC high-power systems. It's a specific, dangerous current range where the fault current is too large for the contactor to interrupt safely,
Right.
but too small to cause the thermal fuse to react instantaneously in that sub-10 millisecond range.
Let's detail the catastrophic fault scenario that lands us right in that zone. Give me an example.
Okay. Let's say the contactor is rated to safely interrupt 2500 amps DC. A fault occurs that is just slightly higher, let's say 3500 amps. Now you have 2 bad scenarios.
Scenario 1.
The BMS detects 3500A and tries to open the contactor. But because the arc energy is higher than its rated capacity, the contactor fails violently. The contacts weld shut or the entire component ruptures, but either way, the fault path is maintained.
And scenario 2.
The BMS is programmed to wait for the fuse to do its job. But at 3,500 amps, a big thermal fuse might need 200 or 300 milliseconds to heat up and clear. And in that 300 milliseconds, 3,500 amps is flowing into the wiring harness, pushing the cable well into its thermal damage limit.
So the cable insulation fails and potentially ignites before the fuse even has a chance to clear.
Precisely. You have a current that is fast enough to destroy the contactor, but too slow to be cleared quickly by the thermal fuse. That's the forbidden zone.
So how does the engineering blueprint mandate closing this incredibly dangerous gap?
The ultimate solution, and it's mandatory for achieving an ASIL-D cutoff security target, is the integration of a pyrofuse. It's a pyrotechnic circuit breaker.
Tell us about this component. This is completely different from a traditional thermal fuse.
Entirely non-thermal, and it's actively controlled. It functions like a sophisticated airbag squib. It receives a digital signal from the safety ECU or the BMS. This signal triggers a small, measured pyrotechnic charge that drives a piston.
And physically severs the connection.
It physically and instantly severs the bus bar connection, an irreversible surgical separation.
And what makes it so powerful for solving this forbidden zone problem?
Its speed and its fixed operating time. It has an action time of less than 2 milliseconds, and that time is completely independent of the magnitude of the fault current.
So it doesn't matter if it's 3,000 amps or 20,000 amps.
Doesn't matter. The pyrofuse acts in milliseconds, guaranteeing isolation long before the cable or the contactor can reach its limit.
So how does the mandated mixed protection strategy use this pyrofuse to completely eliminate the forbidden zone?
The pyrofuse is placed in the main battery disconnect unit, the BDU, right alongside the main contactor. The BMS then implements a two-tiered logic, and this software has to be ASIL-D compliant with full redundancy.
And the logic is?
Simple. 1. If the fault current detected is below the contactor's maximum rated braking capacity, say less than 2500A, the BMS just commands the standard contactor to open normally.
Okay.
2. If the fault current is detected to be above the contactor's limit, so greater than 2500A, the BMS instantly generates the trigger signal for the pyrofuse.
So for every possible fault, the right tool is used.
Exactly. This logic ensures that for every possible fault magnitude, the protection mechanism used is within its safe operating limits. It makes the transition between mechanical cutoff and pyrotechnic cutoff seamless and fast, and it entirely eliminates the forbidden zone.
That requires incredible system integration rigor. The BMS has to react in microseconds to choose the right path.
Absolutely. The decision latency has to be in the microseconds range to safely trigger the pyrofuse, which then operates in milliseconds. This is what guarantees safety for those most catastrophic high current short circuits. And you also have to address the raw current capacity. Given the battery pack can deliver 15 to 20 kiloamps into a hard short, that A-class fuse, whether it's thermal or pyro, must have a rated braking capacity that exceeds 20 Ka at 500 VDC to guarantee successful arc extinction and prevent a fire.
Okay, so we've covered the electrical theory and the coordination strategy. But in this cement mixer environment, physical failure due to vibration is, it's arguably the most common cause of premature death for any component.
Yeah.
We had to talk about the mechanical challenge.
This is where the difference between a compliant component and a failure just waiting to happen becomes so clear. The cement mixer subjects everything to this continuous high-energy random vibration, and the internal components of a fuse are surprisingly vulnerable to it.
How does external vibration damage the inside of a totally sealed fuse?
Well, high-voltage thermal fuses are packed with a specialized quartz sand. It's critical for absorbing the arc energy and rapidly cooling the plasma when the element melts.
Right.
Under long-term, intense vibration, this quartz sand mass begins to compress. It settles, it starts to flow internally, and this flowing process subjects the thin silver fuse element to this abrasive mechanical stress.
So the sand is literally grinding away at the fuse element.
Vibrating it, yes. And this damage increases the internal resistance, which leads to localized heating, thermal runaway, and premature opening under normal current. It's another form of nuisance blowing, but this time it's caused by mechanics, not poor electrical selection.
And how do you combat this?
To combat this, engineers must demand supplier proof of compliance with the most stringent standard there is. ISO 16757-3 specifically test B8 the commercial vehicle profile.
And why is relying on passenger car standards here just a recipe for disaster?
Passenger car vibration profiles are typically much lower in magnitude and shorter in duration. The commercial vehicle standard, TESS V8, it subjects the component to random vibration with exponentially higher power spectral density energy for hundreds of hours across all three axes. If a supplier only provides passenger car data, their product is explicitly forbidden for use in this application. It guarantees structural failure.
The installation process itself must also become a critical safety procedure, not just an assembly step.
The foundation of mechanical integrity is the connection. Engineers have to mandate the use of bolt-down style fuses for all high-power branches.
No blade fuses.
No blade or plug-in fuses. They're completely inappropriate due to the vibration and current density. Furthermore, the installation requires strict, recorded torque adherence. For M8 bolts, it's 10 to 12 newton meters. For M10, 18 to 22. This has to be verified with anti-loosening hardware and documented in the DVPNR process.
And why is that torque so critical?
Poor installation torque leads to localized heating, which causes thermal expansion, which leads to loosening, and eventually connection failure. And finally, the PDU housing itself must be a minimum of IP67 rated to keep out that pervasive conductive cement dust, which can bridge contacts and cause internal short circuits.
Okay, let's touch on the regulatory framework. Functional safety, ISO 26262. When you're developing a component like this from scratch, how does the fuse fit into the required safety analysis?
The fuse is classified as a Type B safety mechanism. In the failure mode, effects, and diagnostic analysis, the FMIDA, we have to quantify failure rates using what are called failure in time, or FIT, values. These are usually provided by the supplier. High-quality fuses are around 5 to 20 FIT.
And the analysis focuses on the two main failure modes and their impact. We've mentioned them, but let's prioritize them under ISO 26262.
The lowest probability but highest severity failure is fail to open, a refusal to clear the arc.
A nightmare.
It directly violates the core safety goal: prevent thermal runaway and high-voltage fire. This risk is mitigated by selecting that 500 VDC rating and having an extreme braking capacity margin.
And the other failure mode.
The higher probability but lower severity failure is premature open, nuisance blowing. While it doesn't cause a fire, it leads to the loss of propulsion, or the ePTO function. It impacts vehicle availability and violates the economic goals of the fleet operator. Both are total non-starters for a commercial vehicle, which reinforces why all those rigorous devarating factors we discussed are so critical.
So all of these theoretical mandates and calculations, they have to be proven in the physical world. This requires a rigorous design verification plan and report, the DVPNR, that's tailored specifically to this commercial vehicle profile.
The DVPNR is the final checkpoint before you sign off for manufacturing. The testing has to validate that the component can handle both the electrical load and the mechanical punishment.
What are the three non-negotiable test categories you'd have in that plan?
First, electrical performance and thermal validation. The key test here is the temperature rise test. You run the fuse at 1.0 times and then 1.3 times its nominal current, but you do it in a hot ambient condition, like 85 degrees C.
And the acceptance criterion.
It's severe. The terminal temperature rise, delta T, must be limited to less than or equal to 50 Kelvin above the ambient temperature. If it runs too hot, the surrounding components and harnesses will suffer. We also, of course, verify the braking capacity at 500 VDC and the maximum short circuit current.
Second, you need the test that validates our KC factor.
The cycling durability test. This simulates that decade of use. For the mixer circuit, this would involve cycling between a high current simulating mixing and a low current simulating idling for over 50,000 cycles. It's an accelerated aging test.
And how do you know if it passed?
The acceptance criterion is very clear. The internal resistance change of the fuse element must be less than or equal to 10% after all 50,000 cycles. If the resistance increases beyond 10%, that signals thermal fatigue and imminent nuisance blowing.
And third, the mechanical and climatic tests.
This is where we verify that compliance with ISO 1750-3 test V8. We subject the mounted component to intense random vibration combined with thermal shock rapidly cycling between minus 40 C and plus 125 C for 1,000 cycles. This confirms that the internal sand doesn't compress, the element doesn't degrade, and the IP67 sealing holds up.
If an engineering team is looking for a partner to supply these rigorously tested components, what does that supplier landscape look like? Who specializes in this?
You need suppliers who really specialize in robust, high DC braking capacity components. Eaton Bussmann is a common favorite for commercial vehicles because they usually have the most comprehensive I2T and cycling life data relevant to fleet operation. Mersin is known for offering some of the highest braking capacities out there, up to 100 kA, which is ideal for extremely high-power battery packs.
Any others?
Companies like PEC, often chosen for Japanese platforms, offer excellent anti-vibration performance. And if an OEM chooses a cost-advantaged supplier, like some of the emerging Asian manufacturers, the engineering team has to take on the burden of performing and certifying that ISO 16750-3 validation themselves. The off-the-shelf data might not meet the commercial vehicle standard. The key takeaway, no matter who you choose, is this. The supplier must prove the product can withstand that commercial vehicle vibration profile. Period.
What a fantastic deep dive. I mean, the engineering rigor required for a component most people never even think about. This is the real difference between a textbook design and a vehicle that reliably works for 1,000,000 kilometers. Let's summarize the 3 core, non-negotiable mandates extracted from this analysis.
First, the mandate for extreme conservative derating. This means using that cyclic loading factor, Kc less than or equal to 0.60 for all high-impact loads. You are deliberately oversizing the component. You're accepting the increased size and cost to buy down the risk of thermal fatigue failure and secure that 10-year, 1,000,000-kilometer warranty.
Second, system-level coordination is mandatory. You have to move beyond just selecting a component and implement that mixed protection strategy, using the BMS to control the transition between the contactor and the actively triggered pyro fuse. That is the only way to surgically eliminate that dangerous coordination dead zone and achieve true ASIL-D functional safety.
And third, the mandate to look beyond electrical. Success hinges on mechanical integrity. This requires demanding strict compliance with the extreme anti-vibration profile of ISO 16750-3, the commercial vehicle profile, and strictly enforcing installation standards. Specifically, mandatory bolt-down connections and recorded torque values, because vibration and poor connection quality are the highest probability causes of field failure.
And here's where it gets really interesting for you, the engineer or the learner listening to this. In an application like this, you aren't just selecting a current rating. You are engaging in predictive material science. You're calculating the total thermodynamic lifetime of a microscopic metal crystal lattice under 10 years of severe mechanical and thermal stress, all to prevent a warranty claim 2 years down the road. So the question for any designer is this. Are you calculating for the current you think you have? Or are you designing for the harsh, cumulative reality of the current? The climate, the vibration, and the fatigue your component will experience. That rigorous calculation is the only barrier between robustness and catastrophic failure.